Hey guys, we're gonna talk about hash tables today. Hash tables are very important for Golang because it's actually when you use the map, it's the underneath, it's the real implementation is the hash map, and there it's using the basically data structure of hash tables. So it gives a lot of advantage. Like usually you work with the maps. Usually most of the operations are the constant time or very close to constant time. Like if you compare with the arrays, arrays are fixed size and it's in the contiguous in the memory, so you can reach it pretty easy and you can store a huge amount of data. The problem with the arrays is comes into place when you want to replace or change or delete element of array. Then is a problem because you need to shift it basically. Or sometimes when you're working with the slices, you don't always reallocate a new place in the memory, but that can be required if you're changing the size of the array as well, so size of the slice. So all these things, so it's also constant time to reach the element of array, but to deleting and also manipulating the data itself, it's the linear time. Big O notation, if you remember, and if you compare to the map is having also arrays like a bucket of arrays, but it's also using the hash functions, and these hash functions are using the hash algorithms to be able to put to data to the correct bucket. And sometimes like some keys of your map can be collide and go into the same bucket, but then you can use the linked list. Then it's still easy to reach the data and manipulate, because deleting this time is not the, you need to change all the structure and the memory address of the data, but you just need to link it from the element of the array linked list you want to delete, and just show the previous items linked to the next one, and then it's done. So it's just constant time, and most of the operations, as long as it's not colliding your data in the buckets, is good. But the Golang is doing pretty well with this in the already implemented map function, so you can use it all the time. We're going to look to differences and all the details. Also, we're going to start implementing it. So let's start. So let's look at some numbers before start coding. When hash table is better than arrays, so we're going to look into arrays and just maps in Golang and a little bit of benchmark, and we're going to implement. So arrays are, as I said before, it's just a constant time, and it's just fixed size list of elements stored contiguously in memory. Accessing an element by index takes constant time, making arrays simple and highly performant. If you look at here, we're just putting student data into the array, and just the random names, and we're gonna eventually get the 500 student's name and put it to the screen, and it takes only 1 millisecond. Quite fast operation. But for maps, it takes a bit longer because it's almost constant time, because all this hash table and hash map operations, it takes a little bit longer, but still it's quite well, and we can reach the same data with the same amount of list. And that is only taking 2 milliseconds. And now let's look something different. And now we need to delete an array. And we use slices this time because it's a dynamic. So we can add the 100,000 students to the array. And we just delete like this. So it has to be, we need to shift the data, and we take the first 500 and then remove the next index, and then we take the rest of the data. And this takes only 50 microseconds. It's not milliseconds, but microseconds. But the strange thing is when we look into the deleting in the maps, it takes constant time, and it's super fast, and it's nanoseconds, not even microseconds, basically, because it doesn't look into the size of the list. So it's not, you can have the billions of the students, but still it will take the same time comparing to arrays. Arrays, if you increase the size, then it's going to increase linearly the performance, and this number is going to go higher. So how we can implement hash tables? We use the buckets. This is the array of buckets, and we use the linked list. And yeah, we just basically add the next common item to the top of the list, and then link them accordingly. And then it's going to be constant time reaching as long as it's not colliding. And collisions can be prevented easily with using the hash function and hash algorithms. And yeah, we're going to start implementing this now. And let's go and implement. Right, guys, let's start and implement. We're going to have the main package. And what we need here is a struct with hash table. And with this, we need to have some functions like insert and delete, and also search. Search will return a boolean, either gonna find it or not gonna able to find it. So for now, let's return false. What else do we need here? So let's put a fixed size. So let's say 10 elements, and we're gonna define an array here, and this array is gonna have nodes. So it's actually, if you remember, here we're gonna have a lot of buckets, and these buckets are gonna have linked lists. So actually, let's go and define the array. So now we have and we can say bucket, and the buckets are gonna have the key and also link to the next bucket. And we also need a hash function, which is gonna indicate to which bucket we need to put to our key. So let's start with the hash function first. So I'm gonna write it here. Just gonna get the key. It's gonna be simple. Gonna start and basically gonna add it to the sum. It has to be integer, and we're gonna return basically mod size, and this has to be integer as well. So this is our hash function. Maybe we can close it like this. And all right, we're gonna use it like this. So we're gonna have an index, and we're gonna go and edit this index, and yeah. But the thing is, now we need to have our bucket, let's say, and this is gonna have the head, and let's have the nodes as well. And this bucket will have operations just like the hash table itself. So let's say bucket, insert, delete, and search. And this is going to return boolean. let's go and use this one as well. And this one has to return, so I'm gonna have the hash as well. Just gonna return the whatever comes from the search. All right, now what is left is let's actually have also another function here, which is new hash table. This doesn't have to be exported as well, and it's going to return the hash table. So what he's going to do is the new hash table and we're going to iterate let's do this as like this. Yeah, and we have to return it. And we're going to use it here. So we have to have hash table, new hash table. Let's say insert Jack, Joe, and we're going to search for Joe. And maybe delete. And search again. So in the second one should return false. All right, apart from this tree function, we are done. Let's continue with this tree. Do here. So let's say there is none of them here, and we're gonna start with adding this one. And so the address of this is this in the memory, and we're gonna have the key, and it's gonna indicate nowhere. And in this second time, we're gonna have Joe, and then this one is actually immediately gonna indicate this one as the next, and it's gonna take over the head. So this is showing here. It has its own address as well, and taking the head, and we add the third one, and third one immediately get this one as next. So then everything will be in order and takes the heads. And lastly, what we do here, we put the address of this to the newest one, and we just put it to top. So that's the whole operation. Go ahead and implement. So we're gonna have a node, new node, and new node is gonna be like this, and we're gonna have the key, and we just put the head to this new bucket, and afterwards we just place the head to do this new bucket. That's it. And if you need to search, we need a current one, and this is going to be our head. So we're going to start searching from the top, and if it's not there, we just switch the current one to the next one, taking this address from here. So for that, we need to iterate, and as long as the current next is not nil, then we're gonna check the current key. If it's equal, then we're gonna return true. If not, then we just change the current one to the next one till it's not nil anymore, and eventually return false if nothing comes. For delete, let's say we're gonna delete the Joe. So we start from this one, the current one, and we check the next one. If the next one is Joe, it's not. Then what we do here, we just take this one as a current one, and we compare the next one again. Oh, it's Joe, then this should be gone. And what we do here, we just, this next address will not go to next anymore. It will go to next. So that's basically it. So we're gonna set current again, and this is gonna be head. As long as the current has a next, then we can start comparing already. Next key, if it is matching, then what we do here is the current next, like we are still in the showing the head. If we start from the top, then it's gonna show the current next. If, and we have to return in that case. If not, then we just change the current to the current next. And that's basically it. So if, by the way, head key is already matching with the key we are trying to delete, then what we need to do here, just the B head has to show the next one, and we return. All right, before we run this, we need to fix two things. First, search has to check the current one. If it's not nil, then it's erased. And also we need to change the hash function and use the for range loop instead. And when we run this for Jack and Joe, in the first search it returns true, and the second one we delete the Joe, so it returns false.